The earth beneath our feet, often perceived as mere dust or an inert substrate, is, in reality, a vibrant and dynamic cosmos, symphony of soil. It is the planet's fundamental foundation, the thin, fragile veneer where lithosphere, atmosphere, hydrosphere, and biosphere converge. This dark, rich layer is far more than just dirt. It is a complex, living entity, a masterpiece of natural engineering that plays a critical and often unsung role in sustaining nearly all terrestrial life. It is the original alchemist, transmuting rock and decaying matter into the very essence of life, orchestrating the grand cycles of nutrients and water that define our world. To appreciate the symphony of soil is to understand its profound complexity. It is a four-part harmony of mineral matter, the remnants of weathered rock, organic matter, the decomposed bodies of once living organisms, water, and air, all housed within a meticulously structured matrix. This physical structure, or soil texture and soil structure, dictates the movement of water and gas, creating the microhabitats for a staggering biodiversity. Within a single teaspoon of healthy soil reside more microorganisms than there are people on Earth, a bustling, microscopic metropolis where constant, silent drama unfolds. This essay will delve into the composition, function, and critical importance of soil, exploring its role as the linchpin of global ecosystems, the regulator of climate, and the bedrock of human civilization, ultimately underscoring the urgent need for its preservation. The perfect soil is a grand composition where four distinct components play their parts to create a medium capable of supporting life. This fundamental structure is the blueprint for fertility and resilience. The mineral component is the product of weathering, a slow, relentless process, physical, chemical, and biological, that breaks down bedrock into its constituent parts: sand, silt, and clay. Sand particles are the largest, allowing for rapid drainage. Clay particles are the smallest, providing immense surface area for chemical reactions and water retention, and silt falls in between. The ideal mixture, known as loam, balances these properties, offering sufficient drainage yet retaining enough moisture and nutrients. Chemically, the mineral fraction, particularly the clay, governs the cation exchange capacity, CEC, the vital mechanism by which positively charged nutrient ions like potassium, K, calcium, Ca, and magnesium, Mg, are held and exchanged with plant roots. This is the soil's chemical pantry, crucial for feeding the world's vegetation. Organic matter, OM, though typically making up only 1% to 6% of the soil's volume, is its chemical and biological engine. When plant and animal residues decompose, they form humus, a stable, dark substance. Humus acts like a molecular glue, binding mineral particles into stable aggregates, improving soil structure, aeration, and infiltration. It dramatically increases the soil's water-holding capacity, absorbing many times its weight in water, which acts as a buffer against drought. More critically, in the modern era, soil organic matter represents a colossal carbon sink. The world's soils hold more carbon than the atmosphere and all plant life combined, making soil health an indispensable factor in mitigating climate change. Soil water is the medium of life, dissolving and transporting nutrients to the roots. The amount of water available to plants is a delicate balance, defined by field capacity, the maximum water the soil can hold after drainage, and the permanent wilting point, the point at which water is held too tightly for plants to access. Excess water must drain to allow air into the pores, while sufficient water must be retained to sustain growth. Furthermore, soil acts as the planet's primary filtration system. As rain and meltwater infiltrate the soil matrix, they are purified by physical and chemical processes before recharging groundwater aquifers, an essential ecosystem service. Like any living system, soil needs to breathe. Soil air fills the pore spaces not occupied by water, providing the essential oxygen necessary for the respiration of roots and the vast microbial community. This continuous gas exchange is critical. Oxygen must enter from the atmosphere to replace the carbon dioxide, CO2, released by subterranean life. When soil becomes compacted, often by heavy machinery or excessive foot traffic, its porous structure is crushed, limiting gas exchange. This creates anoxic conditions that can suffocate roots, reduce nutrient uptake, and shift the microbial community towards anaerobic organisms that produce harmful greenhouse gases like methane, CH4. The living component of soil, the microbiome, is what transforms an inert mix of rock and water into a fertile ecosystem. This hidden world drives the vast majority of biological processes in the soil. The microbiome, unseen architects. The true workhorses of the soil are the single-celled organisms. Bacteria are the primary decomposers, recycling dead organic matter and fixing atmospheric nitrogen, N2, into forms that plants can use. Fungi, particularly mycorrhizal fungi, form a vast, subterranean network of hyphae that extend the effective root area of most plants by hundreds or thousands of times, trading difficult-to-acquire nutrients like phosphorus for plant sugars. This symbiotic relationship is perhaps the most significant biological alliance on Earth, foundational to forest and grassland health. Beyond the microbes are larger, visible creatures. The mesofauna, tiny insects, mites, and nematodes, shred and fragment dead organic matter, making it easier for bacteria and fungi to complete the decomposition process. The macrofauna, most notably the earthworm, are the true mechanical engineers. By burrowing, they create channels for water infiltration and aeration, and by consuming and excreting soil and organic matter, they mix the layers, bioturbation, and produce nutrient-rich castings that stabilize soil structure. The collective activity of these organisms is what defines a healthy, living soil. The rhizosphere is the narrow, dynamic zone immediately surrounding a plant's roots. It is arguably the most biologically intense region on the planet. Plants actively exude carbon-rich substances, sugars, amino acids, from their roots to farm specific microbes in this zone. These microbes, in turn, provide the plant with essential nutrients, disease protection, and growth hormones. The complex, continuous chemical conversation occurring in the rhizosphere exemplifies the exquisite coevolution and interdependence between plants and soil life. The synthesis of composition and life allows soil to perform ecosystem services that are critical not just for local environments but for the entire planetary system. Ecosystem services, the foundation of terrestrial life. Soil is the world's most vital nutrient processing plant. The nitrogen cycle, for example, is almost entirely driven by soil microbes, which convert atmospheric nitrogen into usable nitrates and ammonium, and then back again. This cycle, along with the phosphorus cycle and others, underpins all terrestrial food webs. At a human scale, soil health directly translates to food security, as an estimated 95% of human food production relies either directly or indirectly on the soil. The quality of soil directly impacts the nutrient density, and therefore the human health impact, of the crops it yields. Healthy, well-structured soil functions as a massive, resilient sponge. It allows water to infiltrate rapidly during heavy rainfall, mitigating surface runoff and preventing flash floods. During periods of drought, the high organic matter content allows the soil to hold and slowly release stored moisture, sustaining vegetation. This hydrological regulation is a critical buffer against extreme weather events, moderating local climates and ensuring the consistent supply of clean water. Soil's role in climate is twofold. As previously mentioned, it is an enormous carbon sink. The practice of regenerative agriculture, which focuses on increasing organic matter, is one of the most powerful and practical tools for drawing excess atmospheric carbon dioxide and stabilizing it underground. Conversely, degraded soil can be a source of greenhouse gas emissions. Poorly managed, waterlogged soils can release significant amounts of methane and nitrous oxide, a potent greenhouse gas, emphasizing that soil management is inextricably linked to global climate stability. Despite its resilience, the soil ecosystem is fragile and finite. The speed of its formation, centuries to millennia per inch of topsoil, is vastly slower than the speed of its destruction, leading to a global crisis of soil degradation. Erosion, the stripping away. Erosion, the stripping away of the fertile topsoil by wind and water, is the single greatest threat. Modern, intensive agricultural practices, characterized by tilling and leaving fields bare, expose the soil structure to the elements. Once the topsoil, the most fertile and biologically active layer, is lost, it takes centuries to restore. Historical events like the American Dust Bowl illustrate the devastating societal collapse that can result from the systematic destruction of the soil's integrity. Current estimates suggest that topsoil is being lost globally at rates far exceeding its natural replacement. Beyond physical loss, soil quality suffers from degradation. Compaction by heavy farm machinery destroys the critical pore space, turning spongy, living soil into dense, water-repellent concrete. Chemical imbalances are also a major threat. Improper irrigation in arid regions can lead to salinization, where salts accumulate on the surface, rendering the land infertile. Meanwhile, acidic rainfall and poor fertilizer management can lead to acidification. When degradation is severe and persistent, it can lead to desertification, turning productive land into barren wasteland, a process currently affecting vast areas across the globe. Human activities, particularly urbanization, often permanently seal vast tracts of highly fertile land under concrete, removing them forever from ecological cycles. Furthermore, the application of various chemical contaminants, from persistent pesticides to heavy metals, can poison the soil food web, rendering the land unsafe for food production and disrupting the delicate biochemical cycles performed by beneficial microbes. The good news is that soil is remarkably regenerative, provided humanity commits to acting as responsible stewards. The path forward lies in adopting practices that mimic nature, focusing on the principles of soil health. Principles of soil health. The regenerative approach centers on 4 core principles. 1. Minimize disturbance. Eliminating or drastically reducing tillage, plowing, protects the soil structure and keeps organic matter and microbial communities intact, allowing the fungal networks to thrive. 2. Keep the soil covered. Maintaining a year-round cover of plants, crop residues, or mulch protects the soil from the erosive forces of wind and rain, regulates temperature, and conserves moisture. 3. Maximize living roots. Keeping living roots in the ground for as long as possible feeds the soil microbiome through continuous root exudates, ensuring the engine of nutrient cycling never stalls. 4. Increase diversity. Implementing complex crop rotations and integrating livestock management, managed grazing, breaks disease cycles, enhances nutrient cycling, and promotes a resilient, diverse soil food web. The shift towards regenerative agriculture is gaining global momentum, representing a fundamental paradigm change from extracting maximum yield to actively improving the ecosystem. It is a recognition that a hectare of healthy, carbon-sequestering soil is not only productive but also a public good. Policies and education must follow this recognition, elevating soil from a mere commodity to a finite, critical infrastructure that requires investment and protection. Organizations and governments must prioritize research into soil health, offer incentives for regenerative practices, and raise public awareness of the true value of the earth beneath our feet. The Symphony of Soil is an opus of immense scope and delicate balance, a testament to the intricate workings of nature. It is the silent engine that drives the terrestrial biosphere, providing essential services, from food security and water purification to climate regulation, that are collectively worth trillions of dollars annually. Yet, humanity has often treated this invaluable resource with profound neglect, leading to an alarming rate of degradation globally. Recognizing soil not as dirt but as a living skin is the first, crucial step towards sustainable stewardship. The health of the soil is inextricably linked to the health of the planet and, by extension, to the future of human civilization. By adopting the principles of regenerative agriculture, minimizing disturbance, keeping the ground covered, and nurturing biodiversity, we have the power to restore its vital functions. The future of food, water, and climate stability hinges on our ability to listen to and protect this most fundamental of compositions. The symphony continues, and our role now is to ensure its harmonious and enduring performance for generations to come. Symphony of the Soil. The silent, steady turn of earth. A deep brown choir, giving birth. It hums a note beneath the stone. A quiet love that's only known by patient root and thirsty seed, fulfilling life's most basic need. The ancient dust, a gentle breast, where every weary life can rest. It holds the rain and filters light, converting darkness into bright and vital breath that trees inhale. A faithful bond that cannot fail. From hidden worm to towering pine, it feeds them with a love divine. A grand rehearsal, slow and deep, while all the sleeping creatures sleep. It weaves the cycles, year on year, dispelling every passing fear. We walk upon this velvet floor, and hear the music asking for our quiet reverence and care. A whispered, universal prayer. The soil's dark heart, both rich and free, plays the unending symphony.